Yeah, recording has started.
Okay.
Hi everyone, welcome to Quantum Computer Fundamentals QCF 101. Part 1, we had uh, what you call the beginners or basic quiz. And what I'm going to do is, if you, I will put the link on the screen, and if you can fill in, you want to fill in, you can fill in at this time. Let me just include the uh, so check it out before I say anything, just to make sure that you have the what you call the quiz in your uh, in your. Let me go into the chat window here and put it down here. Just check if you can click on that https colon docs colon google something there. If you are able to reach the quiz, acknowledge, or at least one of you say yes.
Yes, I have it open actually.
Okay, fantastic. Yeah, that should, others should be able to follow. Then there is nothing I need to do on that. I'm recording anyway. So let me go to the shared screen. Okay. So what I want to do is I want to make sure that, of course, all of you may have a version of it, but all I want to make sure is that if you have the version, all you need to do is fill it out. So you see, this is the quiz you have right now, quiz P01B. Okay.
Right.
So you put down your email ID, valid email ID at the top, fill in that, and then uh, the way is, once you put the mail, you can send yourself, and then that will come on your email one way, or keep filling. But at the same time, I would like that you have an email copy of it. So when you say send, just check out if you send. So you uh, can you put your name, email? Were you able to edit it?
Yeah. Yes.
So you put your mail and it is able to accept it. Okay,
Yes.
good. And did you press a send on it at the top?
Uh,
Do you see anything send at the top?
send. Hold on.
But why
I'm
would he
just
send
going.
if he has not yet filled up the quiz?
No,
I
you can get a, okay, you can directly do it. I don't have any problem. Okay, let's just go through it. At the
oh
end of it, you
I
do a send.
yeah yeah I have a
Good.
button called a review and a
Uh-huh.
submit at the way down.
And Prakashji, it's also allowing me to edit the questions. Why is that?
Yeah, because I sent you mine, which is allowing everybody to edit. So for the
Okay.
time being, I have sent it that way. That is the reason I generally send it, and then you edit your own copy and then send it.
Hmm.
That's fine. Right now, it doesn't matter. But we rely on people. So
Hmm.
let's just don't edit the questions, but just answer the questions.
Hmm.
Okay. So you can put your email and then start answering two questions. So let's start with 2 qubits can have Hilbert space.
Hmm.
Select two. So just for argument's sake, what would be it? One,
I
two,
will
three.
select the first one and the third one.
Good. That's correct. And suppose if we select the second one, what's wrong with it?
Well, there's two qubits, right? So each qubit has basically it's a linear
Fantastic.
combination of 0 and 1, right? So there are two of
Good.
them. There will be have four states, right?
Correct. You're right.
Yeah.
The only thing is, if I had, instead of one H2, if I had put one H, then you would be not sure. Hilbert space can be for any dimension, right? Then
Right,
that
right,
would
right,
have
right,
been correct. So, but this is
right.
that is why I specifically put select two, so that you know that you don't get confused. If I say one H can be Hilbert space of any dimension, but
Hmm.
one H2 doesn't mean
Right.
that it is. Okay. Next question. What was part one of quantum computing fundamental about? Select three that best describes your learning. So there will be many answers, many possibilities, but primarily I want to know exactly what you have seen. Did you hear about difference between classical quantum?
Yes, I have
Yes.
one,
Okay,
3, and a 5.
One, 3, and 5. Me too. 1, 3, and 5.
Yeah,
1, 3,
5.
5. Yeah, that's correct. 135 is the best answer. But if you say algorithm or something about um, that is also so, you may be able to take classical algorithm. No, classical. So because I put classical, yeah, that is the reason I put classical there to avoid the confusion.
Okay.
So 135 are correct.
Yeah.
Earlier it used to be algorithm. I edited it basically to make it
Mhm.
classical so that you are not confused, right? So
Mhm.
there is only one answer, and that is 135. Okay. Which one is false?
The third item. Qubits and bits are the same.
Yeah, that's the one which is false. Correct.
Yeah.
Okay. Fourth one, quantum
Beha-
mechanics and computing deal with.
Second one, right? Behavior
Certainly,
of,
second. Yeah.
yeah,
Yeah, second one, behavior of subatomic particle like photon, electron, wave nature, and magnetic flux are electric field,
yeah.
electromagnetic fields. Okay. Then next one, quantum operations are always considered.
This
Yes.
is
You can
just
have
Tensor.
a,
select two. You can select two.
So tensor and unit ray.
Correct.
yeah, that's what I have. I think.
Fantastic. So both of you are on the line. Sign up, sorry, spin up Z basis is represented by matrix. Now
Column
this is
one
a
zero.
column 10. That's correct. So that means second one.
Mhm.
Yeah, second one.
If it was spin down, then you could have done first one.
Yeah.
Okay.
Mm,
And anyway, row is not possible. Row is not the one which is representative of that.
mm.
Okay. So number 2 is right. Okay. Then going to in quantum computation, select all that's false below. So all that is false, but I said only select two. So there are
Mm.
many things wrong. So go over it. You get a qubit state as linear combination of two states 0 and 1. That is true. So it
That's
can't be
correct.
false.
Yeah, yeah, that's
Yeah,
true.
it can't be false.
Yeah,
So ket v is equal to a ket 0 plus b ket 1, where probability density of amplitude r amplitude a square plus b square equal to 1.
That's also
That is
true.
yeah,
True.
that's
true.
also true.
Correct.
Yeah,
Absolutely. Third one, a and b above are complex scalars.
that's also true, right?
That's also true. Correct. Fourth one,
First one, I think I
ket
see the high
v is a
force.
scalar in above.
False.
I I have force there. I selected that one.
Okay. Okay. Let's say there is one more to select, right? So let's see.
Yeah,
Probability
Probability
next
can always be greater than one.
false.
that's force.
False. False. Vector above is considered unitary for all spins or rotations in quantum. That is true.
True.
That's true, right?
So that's true. So only the fourth and the fifth.
Hmm.
Yeah.
Because when we say ket v with the arrow, it means we are talking of a vector, not a scalar.
Hmm.
Mm.
And the probability cannot be more than one. So those two are the false ones. Good. So that clears the doubt on that. Let's go to which of the following are true. Select all. So let's see. Measuring qubit collapses its state randomly to 0 or 1.
That's a true, right?
Hmm.
True. That's correct. True.
Yeah,
Observation and measurements are the same in classical computing.
that's a true. I think.
True. That is true. If it was quantum, it would be different.
Yeah.
Observation is not same as
Yeah.
measurement in quantum computing.
True.
Right,
Yeah,
right, right,
Z is
right,
extra word. I don't think Z should be there, but this is true.
right, right. True.
Then quantum operations are irreversible.
False.
That's a force.
False. Absolutely false. Quantum operation occurs in virtual or hyperspace
True.
called Hilbert space. True.
That's true.
True. Hilbert space is true. If you measure partial in multiple qubits, only one you measure will collapse. The other will what is that? Other will not basically. Other will remain I think we have to go this way. The other, one sec. Other or others will retain their stated if pure supreme. Okay. So basically, as long as they are not entangled, they will retain their states.
Yeah, I think that's true, right?
That is true. That is true.
Yeah.
So I just want to correct it out. Yeah.
Okay.
So
Since
basically,
the
which
someone
of the
has
following? Mhm.
yeah, go ahead. Finish this. Then someone has raised a hand.
Yeah. Who is it? May I know?
Pinky Singh,
Please.
please go ahead.
Yeah, Pinky Singh, go ahead. Speak. Pinky, can you speak? Do you,
Hey,
are you able? Yeah, go ahead.
I'm audible now?
Yeah, you
Yes.
are audible, definitely.
Awesome. So, hi Prakash sir and hi others.
Mhm.
Hi.
I have one question on the previous question where you said the ket
Mhm.
1 or ket 2 or ket v is scalar, or like we said that it is a false. So, but we derive it as in a form of metrics, right?
Mhm.
And it doesn't denote. Uh,
Yeah.
we
Okay. So let me let
like
me let me explain. I got your question. The question was the V. I have pointed there, right? The
correct,
V ket V is a scalar in the above. Okay. So when I say ket V equal to A0, A ket 0 plus B ket 1, uh, is that scalar, right?
correct.
Now, what happens is if I generally talk of a ket V, okay, and if you have a combination of A0 and V0, right? This is nothing but it's a state in between. It can be 0, it can be 1, it can be anything in between.
Correct.
So it's a vector, right? If it was a scalar, if you are taking two vectors, let's say ket V and ket U, and if you find an angle theta between them, then the dot product of the ket V to ket U is a scalar. But ket U and ket V both are vectors.
I see. Okay.
So what happens is the A and B are scalar, they are complex coefficient A and B. Okay. The condition is A square plus B square equal to 1. So even though A and B may be imaginary, like example, it could be 1 plus I, it could be 1 minus I, those are having imaginary, right? So they have a real part, they have imaginary part. When you have what you call amplitude of them and you take a square of each of them, absolute value of each of them, which is again, and then sum of them is 1. So what it means is coefficients can be scalar or should be scalar, you can say, if they are a unitary vector. If they are not unitary vector, then it may not be 1, right? It may still be something more than that, 1.1 or 1.2. So in quantum, any vector of unit length and rotating around the circle with a 0 at the circle point, let's say xy or xyz, whatever we take, it keeps rotating either in the xy plane, yz plane, whatever plane. And since also we are thinking of those vectors as imaginary, some of them, therefore it is a virtual space, we call it. Because if I
Got it.
take xyz real, then I cannot really depict them. Getting it?
Yeah. Yeah. Got
So,
it.
so ket v, ket u, any ket is always a vector. Now the combination, that is, what is the dot product between one vector and another vector? That is different. That's scalar. Okay. So that explains, right? Okay.
Yeah.
That explains. And oh, sorry. Oh gosh, what did I do? Let me just take this off. Let me take off all this. Since I'm in the edit mode, it makes my life miserable. Okay, I have taken that off. Okay, let's go with the uh, measuring cube. Okay, so we did this, right? Which of the following are true already? Measuring qubits collapses its states randomly. That is correct. Observed and measurements mean the same in classical. That is correct. Observer is not same in as measurement in quantum, that's correct. Quantum operations are reversible, that is incorrect. Quantum operations are all reversible. So that means if I do a x naught, then inverse of x naught is again same number, same state, because the inputs are not no more numeric number, they are the states, are basis states, are product states, what we call. Pure states are product states, pure state. So one explanation I'll give you before I get further. If you look at a 2-qubit, okay, 1 qubit we know. 1 qubit has got two state basis states. And it has got what you call alpha 0 or a ket 0 plus b ket 1, whatever you call it, or you can call it alpha ket 0 plus beta ket 1, whatever you call it, right? If you have 2 qubits and they have, again, let's say one has got alpha ket 0 plus beta ket 1 and the other one has, one has alpha ket 0 plus alpha 0 ket 1 plus alpha 1 ket 1, other one has beta 0 ket 1 and beta 1 ket 1. So those are two separate independent in the Hilbert space of C2. That is, two complex coefficients are there for each one of them. But if you make the third one, okay, so when we have two of them, the way it works is we have a bra and ket notation we did earlier. So if I have a alpha 0 and alpha 1, then alpha 0 complex conjugate transpose into alpha 0 plus beta 0 complex conjugate beta 0 is equal to 1, because that is nothing but square, right? If you have complex conjugate coefficient and complex, if you take multiplication of that, that is equal to square. So both of them, alpha 0 complex conjugate alpha 0 is itself equal to square, which is nothing, that is what we call alpha square plus beta square equal to 1. So basically we are representing complex conjugate coefficient multiply both of them, that is equal to x square plus y square equal to ra square plus b square equal to 1. That's the representation. Now, but if you have 2 plus 2, 4 coefficients, and you have got a Hilbert space which is C4, now what happens? Now the combination is, they are not separate. When you are looking from a higher level point of view, from C4 point of view, then if I call them alpha 0, alpha 1, alpha 2, alpha 3, suppose as the coefficient, then alpha 0 square ket 0 plus alpha 1 square ket 1 plus alpha 2 square ket 2 alpha 3 square ket 3, that is equal to 1. So how many coefficients here we have? 4. Yeah, but if we are going by the similar thing what we did, each one of the have to have complex conjugate, right? Like qubit 1 had a complex conjugate. So we did alpha in the early stage. What I said, suppose let me assume that I said v, vector v, what I am showing here, a square plus b square, right? So a square plus b square of this, and same way if there is a CD, c square plus d square, right? A square plus b square plus c square plus d square equal to 1. So now the issue comes down to what, what we explained was, if you have 4 and if you can split it into linear combination, then there is no problem. It is easy. But otherwise, the reason why we got the answer for the 2 single qubit is, if you have 2 variables and if you multiply, you get each of them complex conjugate a plus complex of a square, that is 2. Similarly, b and complex conjugate 4. 4 variables were there, but because we got the a square plus b square equal to 1, so we were able to eliminate the variables. But in the case of 2 qubits independently, you got 2 plus 2. In the case of 2 combined, now you don't have 2 plus 2, you have only 4. So that means you you cannot really have everything pure state, because that is where the problem came last time in entanglement. I was trying to explain that you can have, for a 2 qubit, because you have got 4 plus 4 8 variables, okay, because so the way it works is you have got how many variables for a 2, for a single qubit you have got 2, for 2 qubit you got 4, and that is 2 qubit with 2 independent qubits. But if you combine the 2 qubits, then you have got the 4 of them, and 4 of them together. So there is only one equation that helps you to solve the problem, because you have to have combination of all 4 square equal to 1. You don't have 2 equations like in the 2 independent cases. And therefore, it turns out that when we take the calculation, it comes out that in the case of 2, so what I want to say is, we indicated that you have 1 0 0 0 or 0 0 0 0 0 0 0 1 kind of thing, right? Because you got two. One is 1 0 for ket 0 ket 1, another one ket 0 ket 1 for another one. So 2 plus 2, if you draw one single column matrix, it will be a 4 what do you call states. If you have 4 states, then the pure states can be 1 0 0 0 0. One of the single ones will be pure, all others will be impure.
Okay, just a time check.
Or
Prakash, it's 9 o'clock.
yeah. So yeah, so that what I want to say is, the Bell states, product states plus Bell states together make the whole thing. That Bell states are entangled state, pure states are only as the number of columns, row in the column matrix is there. So for 2 you have got 4, anything other than that is Bell state, okay, or entangled state. So let's go to the, which of the following are true? Select all.
Maybe we should do Q&A now, but people can do that.
Yeah,
And
I'm continuing on Q&A. We'll finish the Q&A and then I'll leave it. Measuring qubits collapse to its state randomly to 1. That we have done, right? This portion we have done.
Yeah, that's what we've done.
Yeah. So we go to electron and photon are different in sense. Both
Third
have
one.
wavelengths.
no, Prakashji, what I meant is
have
Q&A means if the students have any questions, because quiz, it's still half quizzes remaining. So that'll take another 20 minutes. So you want to just see if
It
anybody
won't.
has
It
any
won't take.
questions?
No, it won't have 20 minutes. Yeah, but I'm open to questions. Any questions here?
Yeah, first, why don't you address that? Yeah, because quiz
Yeah.
people can
Do
do on
you
their
have
own.
any specific questions?
No.
Okay.
Uh, Anybody else? Just giving a chance, right?
No.
Okay. So
Okay.
let's continue on that. So the electron and photons are different in the sense both have wavelengths. They are not different. They are
I have a third one.
third
The
one.
third
Okay.
one.
Both
Yeah.
both are subaromatic, but that's correct. Photon is weightless and quantum packets of light. That's third one is photon is weightless. That is correct. That is the big difference.
Yeah, that's a big difference.
Electron has no mass. No, that is wrong. Electron has mass. Photon has no mass, in fact. Photon and electron both move in space. That is correct. So the answer is third. Photon is weightless, quantum packet of light. Okay, packet of light. Next one. The coin has been tossed head tail. Okay, that is one state. Dice can roll and it can have one of the six. 1, 2, 3, 4, 5, 6. Therefore, select one incorrect answer. Select one incorrect answer. Okay. One incorrect answer. Sorry, incorrect answer. So what is the incorrect out of this? Probability of calling head is 5.5, half
That's
correct.
correct. Yeah,
Probability of dice falls facing 2 is 1 by 6. That is correct.
that's correct. Yeah,
Probability of dice falling factor 2 or 3 is 2 by 6.
That's also correct.
That is correct. The joint probability of dice falling facing 2 and coin fall facing head is 1 by 2 into 1 plus 1 by 6. What is that?
Uh,
So half
joint
is
probability.
outside, right? So for
Yeah.
coin probability is half, that is outside. And the other probability is
One
uh,
by
1 by 6, right? So
right.
1 plus 1 by 6 into half. So that is correct. So first one is half, second one is 1 by 12. 1 by 6. But the joint probability is joint. So 1 by 6 into 1 by 2 will be 1 by 12. And I think that is making here 1 half plus. No, this is making half plus 1 by 12. Correct?
It is
It should,
making 7 by 12, right?
yeah, this is making 7 by 12, which is not correct.
I
Right.
think this one is not correct, right? Because the joint
Yeah, it is incorrect.
probability should be, yeah.
See, when we take a joint probability, it is a multiplication, right?
Yeah, exactly. Yeah.
So then this, if it was left at 1 by 2 into 1 by 6, we would have said, yes, this is right. But this is
Yeah.
not. So this is one incorrect. There are other incorrect also, but I have just said select one incorrect. The other one was joint probability of dice facing 2 and Joy's uh, head is 3 by 6.
That is also not correct, I think.
Yeah, that is
This
also
is
not correct.
yeah.
So
And I think the
because
third one is also
so you can take a fourth or fifth, whichever you want. You can take both also, but I only asked you to select one incorrect answer. There are multiple incorrect answers in this.
hmm.
Um, the last one, the possible states are 8 based on the union of two events. That is also correct, but we don't have to incorrect only. We have to take.
Right.
Yeah. So you can have 8 states, but that doesn't mean that that's a probability. It only says about the states. So that's okay. Then the next one, VIBGYOR is acronym for. Now,
Second
why?
one.
Yeah, why this is because when you do a photon, you do in a visible range, and visible range has got these are the colors that you see.
Mm.
So that's the reason I put that, because a lot of time you have ultraviolet and infrared. Okay, both of them are also used. Some of them are used for gamma ray and all that, but we are only focused on the light packets, and that is photon, and that is the visible portion.
Mm.
Next one, state basis unitary transition of a vector in quantum z basis represents either. So z basis we want a spin up or a spin down,
Right.
or rotation of unit vector by angle theta with respect to time n. So basically what happens is, if you have a vector, it is at a position n, and if you do some operation on it, it moves to some other position which is unitary again,
Mm.
but the angle may be different, angle may be theta, and it is at n plus 1 time. So that is valid. First and two
Mm.
are both are correct, whereas third one, none of
Okay.
the above is not valid.
Mhm.
Okay, yeah. So we go to polymatrices or select all correct ones. 2 by 2 matrices xyz whose
That's correct,
individual
right?
matrix square is 1, correct,
Yeah, correct.
whose any two sequential uh, x to y, y to z matrix results in plus minus I third matrix.
That,
So what does it mean?
uh,
Which whose any two? Basically, polymatrix is any whose any two sequential, means x y z is in the sequence, x into y, y into z, z into x, whatever way. It will always result in something like x into y will result in x into y and x into z only we are talking, y into z only we are talking. Anything with respect to z will be third matrix, and that will be plus or minus I.
mm.
Okay. One thing is, you can try is x is equal to 0, 1, 1, 0, and
Zero,
y
one, one,
equal to
zero.
0, no, y equal to 0, 1, 0 I minus I 0. And if you multiply and if you get plus or minus I, then that is what it is.
Yeah, I think
So
it's correct.
basically, that's correct. Yeah. So that's why it's a little bit more complicated. But you remember, x square is 1, y square is I, z square is I, identity.
Yeah.
So the only thing is we have to multiply and see x to z and y to z. And when you do any uh, thing with respect to z, x or y, you are going to get that
Yeah.
minus, plus minus, either I or
Yeah.
minus I. It doesn't matter.
Right.
Then unitary and Hermitian. All poly matrices are unitary and Hermitian.
Right. Right. It's
Now
also
the
correct.
definition, that's correct. Hermitian is what do you call complex conjugate transpose of the matrix is if it is adjacent, then it is
Mhm.
Hermitian. That means self-adjacent. If you have a matrix, whatever matrix, if you take a complex conjugate transpose and that happens to be this what you call same, then it is a then in that case it's Hermitian.
Mhm.
Not same. What it is a complex conjugate transport of it. See, unitary means the multiplication of the two matrices will be equal to identity. So that means if you say unitary, that means it is inverse of the matrix. U equal to inverse U, then it is unitary. But if it is complex conjugate transport of U to U, then so that means what generally for all the quantum matrices, if they satisfy unitary and Hermitian, that's how they are, and that is the polymatrix for 2 dimension. There can be for n dimension also similarly, but we have to figure out what they are. It gets too complex, so people don't get into that too much, except for Trifoliate, Clifford, few gates are there, but other than that, nobody bothers about it because you can always build from, like in the case of gates, classical. If you have a NAND gate, you can do any build anything. Same way, if you have a NOR gate, you can build anything. Same way.
Mhm.
If you have a Tivoli or if you have a C naught and Hadamard, you can build anything. We will come to that later. So here matrix A is Hermitian if it is, select two correct answers. It's self-adjacent, it's inverse of itself, or A equal to A dagger.
Mhm.
First and third are correct. Second is for unitary only. It's not for
Hey,
Hermitian.
sir, one question. So, what is difference between dagger and conjugate?
Okay.
I
No, dagger is a symbol. I could not find the dagger T, in T with the inverse symbol. That is why I put this. That's why I put dagger. Dagger is comp transpose of complex conjugate of the matrix.
got it.
So if you put a star, that is complex conjugate only. But if you put a star and T combine, a star over that T, and then that is together they are called as dagger. There is a dagger symbol used for that. Otherwise, just say complex conjugate, then you can put a star. But it has to be real then in that case. But in case of complex, you have to have complex conjugate transpose for that to be Hermitian, self-adjacent. If the
Got it.
matrix itself is self-adjacent, that means its complex conjugate transport is same as the matrix. That's not same as inverse, okay? Inverse is if you have a matrix, if you do 1 upon that matrix, that is equal to inverse. Or uh, u dagger u equal to I, which is I is the identity matrix. Identity matrix means all diagonal elements are 1. 0, that is 1, 0, 0, 1. If you have 3 dimension, then it is 1, 0, 0, 0, 1, 0, 0, 0, 1. So that is identity. So you can have 2 dimension, 3 dimension, n dimension. Got it?
Got it.
Okay. So the next is sum of two ket vectors B and C is also a
That's the
ket
second one,
vector.
right?
A ket vector.
Yeah, ket vector A Yeah, second one.
Yeah.
So we can eliminate the first and third and fourth and all that.
Right.
Then assume each number on a dice, digital states 1 to 6 represent one electron. How many quantum states do they represent? Assume the linear superposition of all electrons as orthonormal qubits to form a system. So what it means
So the
is,
second one, right?
Yeah. The second
yeah,
one.
2 raised to 6 is
Yeah.
64. That's correct.
Yeah.
The
Yeah.
others are just adding to make confusion. That's all. Correct. So if you have 6 electrons, you will have 2 to the power 6, which is 64 uh, possible, um, what you call in this case, states, basis states. Either basis states or product states. That means pure states. Entangled may be many more, but we'll leave that. That is not the portion we'll deal with right now. Then,
Eh, Sorry,
yeah,
one question on that. So is it right now like what is in practice that we do? It's only the two states for a qubit, or can we have multiple?
no. We what it means is basis states or product or pure states are only 2 per qubit.
Hmm.
If you have one qubit, it means 2. Another qubit means 2. But when you have a system which is system A plus system B combined together, then you have got 4 basis states. But then when you have 4 basis states, that according to us, it should be how many? 2 to the power 2. That means we should have only 4 possible states, right? But then the combination thereof can be many more, and that are not factorizable. That means they are not every product combination. So what happens is normally we are looking for only the unitary and Hermitian matrix, which are self-adjoint. We don't want any other matrices. It doesn't mean there are no other matrices, right? Or there
Right.
are no other vectors. There are many, many vectors. But the vectors we are focused on is for superposition. Similarly, we will be focused on some of the other vectors which are entangled. Now, what is the entangled combination? It could be like your combination when you got a 2 qubit and it is a combined system. Now, in that, you only want the first and the third. You don't care about 2 and 4. You want 2 and 4 to be zero coefficient. Then what happens? Then you got a combination of 1 and third, and both are 1 1, correct? Both are 0 0, sorry, because ket 0 ket 1 ket 0 ket 1. So if I am saying I don't want 2 and 4, I'm just taking the uh, first qubit's 0 state and second qubit 0 state, and rest of the coefficient I am zeroing it. Now how do I separate it out? They are not separable in some sense. You can only separate one at a time. So if you have a column of 1 0 0, you can 1 with 3 0, you can separate. 0 with 1 and 2 zeros, then you can separate. But if you have first one 1 and the third one 1, then you cannot separate it. Because diagonal matrix, when you do a multiplication on the what you call on the matrix basis, column matrix to the other one, then you get more states which are entangled. That's what it means. Getting? I'll come to that. We'll anyway cover that. That is, I covered it in the session part 2. You can go through it once and then let me know. It will be very clear. And if not clear, I'll take another time, sometimes in the class, and then explain the next. So now in the system, about 6 electrons each. If we split the subspace into 3 electrons each, how many column matrices will be needed to represent in each space? So if you have 3 electrons, then what happens?
So we need
3
six.
electron means 3 qubits, right? Every electron is a qubit, which has 2 states.
Yeah.
So,
Yeah.
so you have how
We-
many here? 3 electrons, 3 qubits.
8.
Each one has 2 states. So total states are, basic states are
8. No.
uh, 2 to power 2 to power 2, right?
Yeah, yeah, that's
That is
eight,
equal to
right?
8. 8, yeah.
8.
So,
Yeah.
so you got how many column matrices? Of course, 8. Now, out of that, pure maybe 6. That is different. That's not, we are not bothered about it. At this time, we know that you will need a matrix of 8 here. Okay, then the three bases used are XYZ basis. Then extrapolate to n basis in any direction. So assume Z basis as Ket0, Ket1, and the matrix we use is sigma Z. Will it be applicable to n basis as well? So what is applicable to XYZ? Is it applicable to n? Any direction, any vector n?
I think so, right? Should it be yes, right?
Yes, it is yes. It should be yes. Because you
Yeah,
can align
yeah,
sigma Z with the n, whatever n vector. You just have, because you remember, there is something called rigid movement. That means if you have XYZ
right,
axis,
right,
you move it such a way that you fix the n to n, and that is how it is, and then move along with that. So you cannot move x partially and y partially and z partially. You have to move rigidly the whole thing. And when you move rigidly, that means the vector which is there right now we will align to n and then say then that is our place.
right,
So
right.
therefore it is yes, it is. Um, Logic gates. So there was one. You remember nx plus ny plus nz. We had done one n vector equal to. That is the one which is it represents. Last one. Logic gates. Not last one, but if you are there. Logic gates in quantum are NAND gates,
Uh,
reversible, unitary,
it's a 2 and a 3, reversible and a
2 and 3.
unitary,
That's correct.
right?
Yes, it is reversible and unitary. Perfect. Measurements in quantum. Select to
It's a
Thermal.
deterministic,
statistic. Yeah,
statistical,
statistic,
correct.
and it cannot
And
be copied. Cannot be copied
yes,
and state collapse.
correct. So 2 and 3 are correct.
Right,
Then quantum information size is 2 to the power n bit state at a time, 2 bits at a
right,
time.
right. It's first one, right?
Yeah, first one. Yeah. So if you have got n combination in this one, you can have n. So it is not necessary that you have to have uh, one electron at a time. When you have a mix system which is of consisting of n electrons, all an electron can have their combination in a single sequence. That is a. That is we say a b c up to z like thing, right? A ket 0 plus b ket 1 plus c ket 2 plus d ket uh, 3 and etc etc. We can go to any number as long as the n is finite. So we have to define it is some finite number, not necessarily infinite. As long as it is finite, you can have. So basically, it means one shot we can, if you have algorithm which is having, which can be described as a superposition of n items, then n electrons should suffice to solve that in one shot. You don't have to do the computation again and again. That is the speed of it, right? That's the
Right,
acceleration we get by having that. But it doesn't mean that you cannot have represent two electron the same thing. If you do that, then you are trying to add the reliability. That's how they say that if you have problem of reliability, it's like our GPUs. If you have rows and columns, uh, your matrice is there. So you can use any CPU with any combination. Of course, any thread with any thread combination. You can have parallel threads, streams. So you define as streams, 10 streams or 5 streams or 20 streams. And then one streaming processor can have 4 threads or maybe more just to make it more reliable. So at least if one of them fails, the other one will give you correct answer. So that way you can have more combination, but that doesn't prevent us from having total n. If you have n electron, you can make it 2 raised to n bit state. Yeah, you can
right.
n by 2 and divide by 2 each being represented by 2 electron also you can do to just increase the reliability, but that doesn't mean that you cannot have 2 to the power n. So maximum is what we are counting here. Then going to the Next one. Uh, okay, quantum hardware are robust at
That's the,
even 400 kelvins, or
that's the
very
second
sensitive
one.
even at second one. Yeah. So quantum. So basically, the time to compute is of the order of millisecond, and the so why? Because coherence cannot exist more than a millisecond, and within that millisecond, at microsecond level, you can get computation. So you can get 1,000 computation, maybe 10, 100,000 million computation you can do in less than a millisecond. But then to make that 1 millisecond stability or coherence, you have to struggle. And that is the problem right now we are facing. Either we'll have to extend the millisecond to tens of millisecond and microsecond, nanosecond to microsecond to microsecond to millisecond, or even microsecond should suffice. That should not be a problem. So, in classical theory, what we do a action sequentially at the clock. A upgoing clock or downgoing clock is when we execute. So, if you fetch and execute an instruction, that's what happens, and that's why to do synchronous is harder in quantum because it's too narrow signaling. So you do asynchronous. Currently, we do asynchronous, but we can do it synchronous also. But then that requires a lot more effort. And anyway, we are doing more on probabilistic basis. So that's why it's okay to do what do you call uh, sequential. So sequential, we always talk about sequential combinatorial circuits, right? It can be synchronous, but in our compute, what we do synchronous. Actually, we do everything at the clock of exact clock times. Our program counter increments by one means that exact clock are there. So we do synchronous computing actually in classical. Whereas right now to get to synchronous, we will have to do much more advancement. Currently, it is more of a asynchronous nature. Okay, and the last one, polymetrics is set of 2 by 2 matrix that is correct, but we have to choose false. They are referred as sigma x, sigma y, z, that is correct. Square of
Yeah,
each of them is an ID matrix, that is correct.
that's correct. Yeah,
And the last one, sigma z into plus 1 equal to plus, and sigma z
that's also
minus equal to
correct.
minus. That is incorrect, both of them. It is
Yeah.
inverse, right?
It is
Z,
inverse.
yeah, z on a plus or a z or a minus should give inverse.
It should be Z or it should be sigma Y.
Now it could be sigma x also,
It,
but okay, let me put it on z basis when we are talking, right? So there is a z basis, x basis, y basis.
right.
Okay. So if I am doing on z basis, what I am seeing is plus one, which is actually if I write in terms of z basis, it will be 1 by root 2 of uh, ket 0 plus 1 by root 2 of ket 1. So the plus will be represented by that. Then I apply z basis on it. It will give me 1 by root 2 of ket 0 minus 1 by root 2 of ket 1. And that is again equivalent to minus.
I
That means
think
ket minus.
I think it's only in the number 5 incorrect, right? The minus one is incorrect. The K the minus.
No. See, both of them are wrong, right? 4 and 5 both are wrong.
Both are wrong.
So what I will say is, let me put it. We are taking z basis first of all.
Okay.
Sigma z, we are taking z basis. When you take a z basis, sigma z, if you write a matrix for it, that matrix will be
1 0.
0, 1, 0, 0 minus 1.
Right.
And if you multiply that by plus 1, that is
Yeah.
ket plus, that is equal to 1 by root 2. 1 by root 2, ket 0 plus 1 by root 2 Kit 1. So you are rewriting these in terms of zero basis,
Oh,
z
right.
basis.
Okay.
And if you multiply, then you will get 1 by root 2 minus in between. And if that minus comes, then this cannot be plus, it has to be minus. If you revert back to, so basically when you multiply by operator z or poly z on um, any vector, in this case the vector we have represented as +1, and +1 is always, so we have got 6 vectors we know. One is ket 0, ket 1, one is plus minus, one is I minus I. These are the standard XYZ usable, and they have a, because the probability of is half in each case, it gets on to 1 by root 2. Half plus half is 1, but half when you are putting on a basis which is different, then it gets different.
Right.
So if I take a ket 0, ket 1, we know either it is 0, it's up or down, but it is left or right or up or left or right, or if it is inside the page or outside the page, they also represent IO, and you up and down, they represent left, right. Arbitrary, they put anything, but essentially this is the standard. Plus minus 0, 1, I minus I. Those are the 6 standard ones you use, and there are 4 more which I will describe later, entangled, plus 5, minus 5, plus psi and minus psi. This 6 plus 4, 10 are the real, actually we have to remember what they mean. It's like a number calculation, 1, 2, 3, 4, 5, 6. Same way we have to know what is ket 0, ket 1. It's a bit tricky, hard to remember. But if you don't understand that, then we cannot move. That's the reason I was very insisting on at least do this exercise quiz so that we can get over it. I think that should suffice for the day. At least you got something and you can submit it, okay? If you have got it, you can submit it, because what is happening is I am collecting all the responses here. And if there is anything wrong from my side, you can point out. I'm not a perfect day, because all of us tend to make mistakes. So I'm just trying to make sure that you people are all up to date, and hopefully that will close with this today. And one thing is, if you have seen the, let me just give you, let me share again, stop share and reshare to give you some idea. One of the folders I want to show, actually, that's all I want to do. So I want to stop sharing. No, so at this time I'll stop the recording.